So, all right, it's after 1:30, so I'm going to go ahead and start. I'm pleased at the number of people who are here. I hope I'm not going to be too technical, but I think you'll enjoy it. And if you have questions as I give the talk, then please feel free to ask, as we did yesterday, if you attended yesterday's talk. Let me get my controller here working. So this talk is more laziness in lists. It's kind of a follow-on to the talk I gave yesterday. And I'm coming up with alternate titles for this. And so far the best one I have is Perl 6 lists, the good, the ugly, and the... And I'm trying to figure out what to put in after ugly, but it has to do something with insanity. So, and I thought about just leaving a whatever star, but I wasn't going to necessarily do that. So, first of all, I'll start with an introduction and recap. In yesterday's talk, I focused on lists and arrays. We're going to do more of that today, but at some of the more deeper details. We covered list interpolation basics, some basics about infinite lists, talked about how arrays work, parcels, Slurpee lists, and list of lists. This talk covers more of the internal details of the Perl 6 aggregates. So this talk covers iterables and iterators, a little bit of hash basics, and if there's time permitting, I'll go into a little bit about captures, but I'm somehow doubtful that I'll get that far. So we'll see, because I already know there's like 40 slides in this presentation, so it's going to be hard to do in 40 minutes. More view from last time. If you go and read the synopses, which are the current Perl 6 language design documents, and you read what they have to say about lists, they're very out of date, so don't trust anything you read there. If you have a question, you can email me, ask on the channel, a variety of things, until I get what is now in these presentations into the synopses. Yes. Yes, you probably can't see it, but there's a URL at the bottom. I'm going to add the talk URL to the page on the GAPC schedule, so that you'll be able to get to the slides. Right here. I'll give you just a couple of minutes here. There. That's the URL for the slides, as they existed 20 minutes ago. I made a couple of changes here. So the current synopses are out of date, so you can't really trust what they have to say. We have these things called lists. They are mutable sequences of objects, and it's the sequence that's mutable, not necessarily the objects. They can be mutable or immutable. Lists are lazy in Perl 6, and what that means is they have a reified part, or the part that we've already figured out, and they have a generator part, which is the part we have yet to figure out. Reification is what we call the process of creating new elements when they're needed. So if we have a list that has 10 elements and we ask for element number 15, then it goes to the generator part to get elements 11 through 15 so that it can return it. And that's what we mean by on-demand or done lazily. Lists in Perl 6 can be infinite. It's possible to create lists that have an infinite number of elements, and the laziness is what allows us to do that. It's conceptually infinite, but we don't eat up space for things until we actually ask them. Arrays are a special type of list. They're a list of scalar containers. The things you put into an array are copies of values as opposed to being the values themselves. And if you do any sort of list assignment in Perl 6, it's done eagerly. It kind of gets rid of laziness if you're assigning to a list. In yesterday's talk, I talked about flattening and non-flattening contexts. Flattening contexts will take parcels and interpolate them into the list so that it acts like what Perl 5 did. If you had things in parentheses, it tended to flatten them out. There's also a list context that will take anything and give you its list representation. There's an item context that prevents things from being flattened or interpolated. And there's a list of list contexts, that's what LOL stands for, that will take parcels and turn them into items that don't flatten. And we have ways in subroutines to be able to say that we want a list of arguments flattened or that we want a list of arguments not flattened. And so those are the Slurpee with a single star and the list of lists with double stars to be able to do that. So before I go on, any questions? Anything somebody wants me to cover real quick? No? Yes? If
1, 2, 3, 4.
Yes.
So the dot, the 1, 2, 3, 4, it's going to reify that one should just be nice.
Yes.
Dots the imaginary.
And that actually needs to be fixed even further. So the question is, if you do something like this, .inf, then what you get back is it did the initialization there. So we've created J, which is an infinite array consisting of the values 1 through infinity. And when the interactive mode went to display the value that came back, it went to display it. Earlier versions of Rakudo would just put ... No, they didn't. They didn't go forever, but they would just put ... So you had no idea what you got. So when the printer part gets to the point of saying, "Oh, I have an infinite list," what it currently does is it says, "Make sure I have about 4 elements of that list to display before displaying the ... So at least you have some idea of the sequence that you're getting. I'm going to want to change that so that it displays all of the values it already knows about, and then do that. And if there aren't enough of those, then extend it. It did some weird things for me as I was preparing a slide yesterday, so I know there's a bug there that needs to be fixed. But yes, it tries to give you an idea of what your infinite sequence is. At that point, yes. One of the things about laziness, and we mentioned it yesterday, is that by default, you don't have an awful lot of control over it. We're probably going to, you can't easily say, don't evaluate this. Something can go and ask for something and be able to do that. There will probably be some constructs added that will let you say, this needs to be really, really lazy, and I really don't want you to do things unless you have to, but we haven't defined that yet. Wrong window. All right. Oh, and then parcels. Parcels represent syntactic groups of objects. So here we have 2 parcels. We have one parcel containing hello and A, the array A. And we have another parcel containing 1, 2, that parcel, fraction 5/8, and a hash %h. Okay, and they flatten in some contexts and they itemize in others. One of the things that I just wanted to repeat, because we'll see it from time to time in this talk, is that it's the comma that constructs a parcel and not the parens. Right? So if you say parentheses XYZ, close parentheses, a lot of people say, oh, that's a parcel containing XYZ. And that's not what it is. The parens are just for grouping. Just like if I said parentheses 2 plus 3, close parentheses, that's a 5. It's not a parcel containing a 5. Right? So it's the comma that creates a parcel. If you need a parcel with just one item, you use a trailing comma. And that gives you a parcel with just one item. The exception to that rule is that an empty parcel can be created by just doing 2 parents. That gives you an empty parcel. So, I'm sorry, this last one?
The first one. That would be consistent with the last one.
Not only that, you can make it a parcel, but you're constantly packing and unpacking them then.
So it becomes
Yeah. So it's much easier if it's just not a parcel. Like if I'm doing a math formula where I say 3 plus paren A times 4, okay. I don't want it to become a parcel just because I put the parens there. And then we have to have a leading comma thing and stuff like it. This doesn't occur that often, so it's bad that we have the exception. We haven't figured out how to fix it yet. Talk to that guy. I just implement what he says to do and tell him what he says to do is nuts. But so alrighty, and then try and implement it anyway and say, oh well, that wasn't so nuts after all. So most list operations will flatten parcels. So here I have an array with 2 elements, 2 and 3, another array with 2 strings, F and G. And if I were to put these inside of parcels and ask for how many elements it is, then it flattens it out like Perl would. And if I ask for the 5th one, I'm going to get the 5th one after flattening and not before. Actually, now that I think about it, I don't know where this occurred. That's a bug in Rakudo, I believe. So let me... No, I could do that. My B equals FG. Since I have the person who makes these decisions here as the captive audience, you could...
I'm a little distracted trying to rearrange my desktop to
24 by 768. Okay. Well, this will be real quick. So, Larry, do you agree with the slide that that should be 7? That these should flatten out to give me 7 elements and not the element should be 2 because there's 2 things in the parcel.
Most of our list-ish
Operations on parcels flatten.
will flatten. Yeah.
So great. So Rakudo has that
So you
wrong.
did it right.
So my slide is right, Rakudo's wrong.
Oh, yeah.
I don't know when that bug entered, but it will leave. And it will leave by next Tuesday when the next release is. What's interesting is apparently we don't have a spec test for it. That bugs me. We don't have a regression test for that. So I just noticed that last week. All right, so if you need to explicitly flatten, you can do .flat. If you want to keep the parcels so they don't flatten, then you can ask for a list of lists and they won't flatten. So we can go from there. All right, so iteration and laziness. So this is the part where we're going to get into the guts of how iteration and laziness actually work in Rakudo and some of the reasons why we had to get there. Parts of it are scary and pretty, there's a lot of details that goes into it. In getting to this point, I've gone through at least 5 different implementations that I know of. Each one was thrown out because it was obviously wrong, which meant we had to change the spec, which begat a new implementation, which we discovered was wrong in other ways, and so forth. I have some examples of why that occurred. So the key feature for iterators is to note that laziness can introduce many action at a distance effects. And I'm going to show a couple of examples here. So we had a lot of false starts. One of them is that when implementing iterators, you can either do things like iterate and throw away the things you've already iterated, like a pipeline filter. And that results in data loss at a distance. Or you can keep everything, but if you're trying to do something like a pipeline and you're processing 1 million elements, you don't want to keep the first 900,000 as you're working on the 900,001th if you're actually doing it like a filter or pipeline. So that's bad for pipelines and memory usage. So the key insight that was developed is that our lists are mutable and our iterators act immutable. And by that means is that once they come up with values, they don't ever change their idea of what those values were. Okay, so I'm going to open a block here with a no worries pragma, which means that for the next few slides, if it doesn't make any sense to you or you don't really know what's going on, don't worry about it. All right? So there's a open block and we'll be in this. So here's the basic challenge of iterators. So one of the goals and one of the exercises that I would do on the channel is to say, let's write a function like the map function that is going to process all of the elements of a list and apply a block to it. Okay, so map generally acts like a filter in a pipeline. So here's a naive implementation. All right, so in this implementation, we have this subroutine called myMap, and we'll take a list as an argument and a block as an argument, and then we're going to count through the elements of the list as we go through it. And as we go through each index, then up to the number of elements in the list, then we'll process the element from the list through the block and put it on the results, and when we're done, we'll return the results. All right? There's a couple of things to note about this implementation. First of all, it's eager. It's not lazy, because map is going to process all of the elements before it returns. All right? And that's okay. It's irrelevant to the point that I'm going to make, but I did want to note it. It's also eager because you asked for how many elements are in the list. So once you ask a list, how many elements do you have, it's going to go start generating them all so it can find out how many there are. So that's one thing to note about this particular function. Another question that often comes up is they say, well, if you're doing a while loop here, why not just put a for loop there to iterate through the elements and not do it with the while loop and let for take care of it? Well, the answer is that in Perl 6, map and for are the same thing. So you can't use for to do it because that's what you're trying to implement. All right? And so just as a side note to this, in Perl 6, if you say for list block, where you're saying apply this block to all of the elements of list, that's exactly the same, at least in Rakudo, as if you wrote this. So make a parcel out of a list, or make a parcel containing the list, and apply this block to every element of that particular list. They are exactly the same. Because of, good question. So why does it have to be a parcel? And the answer is because of this situation. So if I have my x equals something, whatever it may happen to be, and I say for $x block, how many iterations will that do? So we'll do 1. And so the equivalent map, because it's a scalar, so it won't flatten. So therefore, it's like that. By putting it in the parcel, it doesn't flatten. If I left it without the parcel, then what I'm actually doing is mapping on X itself. And if it's a list, that's applying map directly to the list. So that's a good question. The no worries pragma is still in effect. Yes, it is the one for list.
So you could, for an array, leave out the parcel.
Yeah, if you have this situation, that's a very good question. So the question is, if you have an array and you want it to flatten through a map, can you do it? And the answer is yes. So if I have my x equals 1.10, like so that creates an array, and it's in a scalar variable. And if I want to do something to that, like print out each element, that will map over all of the elements of X, because what I'm actually invoking it on is the array itself. And the fact that it's in a scalar is lost by the time you send the message.
I think we have the same question I had with the actual slide. That wouldn't matter with that.
Yeah, but it wouldn't matter there, but the compiler doesn't figure that out. It probably could to save the creation of the parcel.
You have it because it wasn't before, though, right?
Yeah, I wanted whatever I put inside the parents to exactly match there. So if that was a $sign variable, then I would need the comma to make it a parcel.
Code for code equivalence.
Yes.
Okay, I didn't mention.
Yeah, and if you actually go and look at the code that generates the for list, you'll see that it actually creates a parcel, calls map on it.
Does it actually translate the syntax like that?
I translate it to the more language format now, and then get a list operator.
More.
Or gives you get a list context before, you get a list context, you say map block list. Instead of using the method. This is a, I think, more equivalent.
So far so Larry's point is that we could make it into the functional form as a list where it's a list that's passed as a Slurpee. And I mean, then you're actually creating an extra level of indirection for the Slurpee that you're shifting off of, you're processing the Slurpee. So all of your elements that you're going through have to go through this Slurpee because it's lazy and flattening and a variety of things like that. So you're adding an extra level of indirection. And also, in general, we've tended to try to make our functions rely on our methods, not our methods rely on our functions. Right. So, okay, still no worries on. So, if you decide that this talk is not for you and you leave, I'm not offended. So that's fine. Alrighty. Map and for are equivalent. Okay, so this is the version that we just saw where we're using an index variable to count through all of the elements. Let's try a different one. Oh, no, let's look at what happens in this particular case and why it can be problematic. So I have a file handle here, and I'm going to read all the lines from the file handle, and that's going to occur lazily. And I'm going to apply this block to all of the lines that I read from that particular file. So when we're inside of this, this function here, and we're doing that, the first thing we do is ask for the number of elements. So we go and we get all the lines of the file into this array called list. And if that file was 1,000,000 lines long, we just filled out list with 1,000,000 elements before we processed any of them. And now we're going to start processing them. And as we process them, what happens to them? They stay around, right? We're not throwing them away. So the problem is that list ends up holding all the lines, and it's not acting like a pipeline filter. Normally, if we think of like a Unix pipeline, we process something, do something to it, and we throw it away. And that's really what we want map and for to kind of act like. We don't want them to keep everything that they processed around when they're done with them. So let's try and fix that. Let's try doing a shift instead of going through all of them, so that as we process them, we're actually taking them off of list and do it that way. So for this particular function, we'll take our list that we want to do, the block we want to apply, and we'll, as long as there are more elements in the list, we're going to shift the next element off the list, send it to the block, and push the result of that onto our result list and return it. So now, when we process all of the lines of this file, as we read in the lines, which is what will happen when we test to see if there's any more, we will shift them off and push on the results. So now it's acting like a pipeline. Does that make sense? Any questions? But, so the lines are discarded, but now what about this form? Okay, so this is the same version I had with the shift. So I'm going to say, get all the lines of the file into the lines, and now I want to process this block on all those lines. What happens to that array? You actually shift off all the elements of that array as you're going through and doing it. So when you get out of this, now this array is empty because it shifted them all off. And that is probably not what the programmer expected. Certainly not if they're a Perl 5 programmer. All right? So we have that particular situation. So this one's not going to work. So we have this kind of contradiction between sometimes we're going to go through all the elements and we want to keep them around because they're bound somewhere. And sometimes we're going to go through all the elements and we don't want them to be kept around because they're not bound. And so it's kind of this bound versus unbound thing. If it's been bound to a variable somewhere, we want to keep it. But if it hasn't, we want it to be discarded as we process it. And, you know, you can do things like, well, let's make a copy before we process it. That kind of gets, you know, away from what we're trying to do, which is to not eat up lots of memory in doing this and things like that. Okay, so now we've reached the end of our no worries block. If you didn't understand all of that, don't worry about it. After this part, you can panic all you want. All right. So the implementation requirements that we have for Perl 6's list and iterator model is that lists and iterators must be able to handle varying degrees of laziness and eagerness, varying degrees of finiteness and infinite list. Sometimes we have things that interpolate and sometimes they don't interpolate. Sometimes they flatten and sometimes we want to preserve the structures. Sometimes the lists are bound and they're unbound, and sometimes we are aliasing to elements where we want our lists to actually refer to the original element, and sometimes we want them to be copied. Oh, and by the way, the programmer shouldn't be burdened with any of the details of knowing what's going on here. It all happens generally dynamically, so you're limited in terms of the static analysis you can do, and because it's a core feature of Perl 6, all of this has to be really fast. This is why we had 5 different things. This is how I often looked when we discovered something that wouldn't work. By the way, just for the record, I blame this guy, if that wasn't obvious already. After all, Perl philosophy is simply to torment the implementers, that would be me, on behalf of the user. I love that quote. Well, it has always been Perl philosophy. That has always been Perl philosophy. And, I mean, going back to my early days of Perl 4, what I really liked is the fact that I was no longer tormented by the things that all the other languages tormented me to do. So that was there. So the solution that we came up with finally, after many failed designs, is what we call immutable iterators, and that's what I'm going to be talking about. Iterators are like cursors, and they act like cursors. So here are our base classes. We have iterable. These are things that can be iterated. So they're objects that can produce an iterator when you need them to. They have an iterator method that does that. And iterables tend to interpolate in list contexts, unless they're in a container that says don't interpolate. All right? And so examples of iterables include lists, arrays, lists of lists, and so on. File handle is not iterable, but if you ask a file handle for its lines, that's a list, which is iterable. All right, so files was one of the weird things. Early versions of the Perl 6 specification really had trouble with iterators, flattening, and all this kind of stuff. And what the whole goal of what I'm describing and that we came up with is your iterators are really hidden. And that's what will happen. That's what does happen. Okay, the versions of map that were there weren't to demonstrate how we solve laziness. They were to demonstrate the fact that bound and unbound. Okay. Alrighty, so these are the other ones. I should have put in here hash is an iterable. Also, you can iterate over a hash, and you get a list of pairs. And there's a few others, but I need to update my slide for that. Then we have the iterator base class. It's an abstract. Both of these are really abstract classes that we expect you not to use them directly. It inherits from iterables. So every iterator is itself iterable, because the key thing that makes something iterable is that it can return an iterator. So an iterator, when it's asked for an iterator, just says self. Just returns itself, and there you go. These are the objects that perform the iteration. Their main method is something called reify that produces values, and we're going to walk through that here. And usually, iterators are wrapped by some sort of a list. So, for example, a file handle, if you're reading from a file, there's an iterator down there that's doing all the work, but what you see is a list of lines, and you can treat it like a list of lines to do things with. Three of the common iterators are list iterator to iterate elements of a list, a map iterator which applies a block to a list. This is the part that handles laziness and block application. There's a construct in Perl 6 called gather take, which allows you to start a subroutine, and then it will only produce values that get returned in a sequence when you explicitly say take, and that happens lazily. So there's a gather iterator for that. And we're going to look at a couple of examples. To look at it from a hierarchy perspective, at the top of the hierarchy, there's actually another class above this, but start with any. Any is our base class for most common objects. It's kind of the standard undefined type, and has the methods that all the different objects are. There's a subclass of that called cool, which is common object-oriented library or something like that. It's basically the this is the class of objects that tend to like to act like others. So string and int and list. Since you can use a list like a number, it's in cool. Since you can use a string like a number, it's in cool, and that's the thing that handles that bridging.
Perl 5 scalars.
Yeah, Perl 5 scalars. That's a good way of doing it. Then there's iterable, which is from cool, and the iterables are things like list, which includes array and list of lists and so forth. And then the iterator is a subclass of that, and then we have the various types of iterators. If you're wondering about that one, I have a set of slides on it in a little bit. Okay, so for an iterator, the key method is the reify method, and you pass it a thing that says how many elements do you need. So you could do an iterator where you always get one element at a time. But if you do that at a method call level, that means every time you want to get one element, you're going and fetching one element. And if you need 1,000 of them, you're going to do 1,000 method calls just to do it. So it's parameterized, that you can request, I need 1,000 elements. And that way it can process them quickly and return you 1,000 elements in a single method call instead of having to do a bunch of them to make that happen. When you call reify, what you get back is a parcel of all the reified values that the iterator produced, and the iterator puts in that parcel any subsequent iterators that will be needed to continue getting more elements. It's going to be a chain, and we'll illustrate that in a second. If you request a certain number of elements, an iterator is allowed to go fewer or greater than what you request. In other words, the iterator kind of controls. You say, I want 1,000 elements, but if it says, I'm going to go ahead and produce 2,000, it can choose to do that. Now, it depends on what it's iterating as to whether it will or not, but it's allowed to work ahead if it thinks that that will be more optimal in the long run.
Like standard in buffering.
Yeah, like standard in buffering.
Would it return all 2,000 or just the first?
It will return all 2,000. Okay, but list, normally you're not dealing with these. List already knows how to deal with that. Okay, you can specify special values. Oh, I turned off my pointer. You can specify special values in the thing like star. The whatever star means give me whatever, which basically tells an iterator, go get me some more elements. I don't care how many. It's got to be at least one. But get me some elements, whatever you think is appropriate, and give them back to me. And you can do inf, which says give me everything you have left, or signal to me somehow that would be silly. In general, most programmers don't have to interact directly with iterator. One of the earlier versions of Rakudo would tend to return iterators that programmers could see, and it caused no end of problems because people couldn't understand. So we really want that hidden. So they're usually managed internally inside of list objects. The key point about when we talk about immutable iterators is if you have an iterator, it's got some lazy things that it has left to generate, and you ask it to reify something, it does it, and it suddenly becomes immutable at that point. It will not change from that point on. It's kind of like, if you think of it in terms of physics, it's like you collapsed a wave, right? And you're stuck in that universe for that particular iterator. What it does is it returns the same parcel of values, so it's going to generate some values, And if you ask it to reify again, it's going to give you the same thing it did before. But one of the things it gives you is a handle to the next iterator in the sequence, which will be responsible for getting more values later. So further list generation is handled by iterators in the return parcel. It's kind of like a linked list with head and tail portions, or Lisp's Karakutter model, like so. That what you're doing is you're basically saying, give me this part, make that fixed forever, and the iterator defers any other generation to another iterator, usually the same type. So the generic pattern for implementing an iterator's reify method looks something like this. You define your iterator, its subclass from iterator. It has a reified attribute that you're going to fill in. When the iterator is asked to reify something, you check to see if you already did so. If you didn't do so, then you do so by generating your in elements, and you bind this parameter to whatever you generated and a follow-on iterator if one is needed, and then when you're done, you return it. So the first time you call, you're going to go through the unless portion and generate some elements. Every subsequent call, you're going to return what you did before. No matter what n is, no matter what it is, it's kind of like, I already did this, I'm stuck. This is what you get. If you want more, then you need to go follow the iterator I gave back to you and ask them. So you end up with this chain of iterators as you go reifying elements, with each one pointing to the next one. Now the nice thing about that is, if you think back to our buffering example where we were accidentally buffering them, if I go and ask an iterator for a certain number of elements, and I get through all of them and I get to the next iterator, and I go asking for the elements, and I lose the last reference to the first iterator that was there, it's garbage collected. But if anything else has a reference to that iterator, those elements are still waiting there to be picked up by whatever else it was before. Okay? So we get to use garbage collection and the built-in fact of following references to manage when it's safe to lose the elements. The binding problem kind of goes away at that particular point. So the listIter class handles most of the iteration and reification tasks for lists. This is the nasty one. Here, we can go and look at it real quick. I can put the no worries pragma back in, but some panic is sometimes good. Source core listiter.pm. Okay, so the iterator is written in Perl 6. And in fact, all of the core libraries are written in Perl 6. There are a few places where, for efficiency reasons, we do things with some lower level special opcodes. And you can see those by things that begin with NQP or PIR. But the code there for doing reify is that long. And this is by far the most complex iterator that we have. So what it does is, it handles lazy generation of values. It handles if you're iterating over a list and it's got other iterables in the middle of it, the listiter is the thing that does the interpolation. And the way that it does that is it's going along doing its generating, and it comes across an element that's an iterable. And it says, oh, I'm supposed to interpolate at this point because it's an iterable. And so it asks the iterable for its iterator, and it asks that iterator to do a reify of some elements, and whatever it gets back in the parcel, it just splices in place and then keeps going, start processing those. So it just does a lot of splicing. And so as you're iterating, a lot of intermediate objects all of a sudden start disappearing because you're taking and replacing the large aggregate with the elements that it was aggregating as you're doing your flattening. Iterables will also flatten parcels if you're a flattening sort of thing. There's a special value called nil, which if found in a list is simply means nothing. It doesn't generate anything, so it removes those. And it also handles the eagerness and infinity constraints. And here's kind of the process that it goes through to handle reification. We have a special low-level array called rest. So this is a low-level array at the level of our virtual machine. It's not a Perl 6 array that is lazy and everything like that. This is literally just an array that we can grow and resize, but doesn't have laziness or any of the other features. So we start shifting things from there. We start building a parcel of things that aren't being interpolated and aren't being processed, the things we are going to return back. The listiter, as it produces this parcel, it also has a link to a parent container, where it can say, I produced these things and you're responsible. You told me I'm supposed to tell you when it happened. And so you can go store them. And so it does a callback to do that. And that's what allows a list, which is the thing holding the list iterator, to put the newly reified elements into its list of reified elements. Okay. Then we create a new list iterator to handle whatever other lazy part is still left to be done, and we return it to the caller, and we're done, and that's how it works. So the list class, a list object, has a low-level array of things that have already been reified. It has a list iter chain for anything that hasn't yet been reified, that is still being done lazy. This is the class that implements shift, push, pop, unshift, all of the things that you would do to a sequence of items. So the list is mutable. You can add things to the beginning, take things off the end. I should have put splice in there. You can splice in the middle. You can index for a specific location, things like that. And the key thing is that a list, when it's managing this list iter chain, it's the thing that gets the callbacks whenever new values are generated, so it knows I'm supposed to put them as being reified. There's a special method. I noticed this was asked several times yesterday on IRC and a few things. What if you want to know how much has been reified? You can ask a list how many elements it has, but it goes and generates all the elements. What if you just want to know, well, how many have you got already? And there's a gimme method for that. And the gimme method is a way to tell a list, make sure that you've worked ahead at least to this point. Give me at least this many elements. And we couldn't come up with a better name than gimme, so it stuck. So when you call gimme on a list, it ensures that at least n elements of a list have been reified. So it looks at that number, and if it's already reified that many, it just says, okay, I'm done. If it hasn't done that, then it tells its list iterator, I need this many more elements, and it goes through and follows the chain of list iterators and manages them until it has enough elements, at which point it returns. And the last thing that it does is it says how many are actually been reified. So that, that answers the question that the callers want to know, which is how many have you already got. So here's an example. I've created an infinite list of the Fibonacci sequence. If I ask for the eighth that element at index 8 in the array, then it comes back and says it's number 34. So if I ask that array, how many have you generated? And I give it 0, which means I don't want you to generate any more, right? Because you already have 0. So just tell me how many you've already got. It'll come back and it'll say 9. And the reason it says 9, its indexes 0 through 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8th is the one at index 8 is the 9th element. Then I can tell A, go ahead and give me 50 elements. So that actually generates all the indices from 0 to 49, fills it in. And now, anytime I ask for an element prior to index 50, I'll get it back almost immediately. There's no generation that has to take place. It's already been memoized. It's already been recorded in the array. And so it's very, very fast. So if I know that I'm going to be doing a lot of lookups at later elements, I can tell the list, compute a bunch of these right now really fast so that my later lookups will be quicker. Instead of having it go and generate one, and then I'll come back and ask for the next one, so it has to go and generate another one and do it slowly. You can tell it to pre-cache a bunch of values and then use them directly.
And in fact, the CPU cache is better this way.
Yes, lots of things are better. You're reducing the number of method calls. You're doing all sorts of stuff. Because they return different things. I'm sorry, the question is why not just call it reify? Because if I call reify on an iterator, it gives me back the things that were reified. If I call gimme on a list, it tells me how many have already been reified. So since they do two different things, they should have different names. And in this case, they're really different. The Maplter class handles map in 4. So it takes a list that it manages another list iterator to work with, and it iterates over that list, and every time it gets elements from the list, it applies a block to it. Now, unlike Perl 5, I don't know about unlike, anyway, in Perl 6, the block can have multiple arguments. The signature of the block can actually have 2, 3, however many arguments you want. And the map iterator will look at the signature of the block to figure out how many things it needs to get to the list to send to the block. And that's what enables this sort of stuff to work. Let's close that. So that's how we can do something like this. For list pointing to A, B, do something. that grabs elements out of list 2 at a time. Right? So it'll grab one element from list and put it in $A, and another element in list and put it in $B, and invoke the block. Now, the key point to noticing or to understanding how that works, if you're not familiar with Perl 6, is to note that the part beginning with the arrow is the block. The arrow initiates a signature for the block. It's called a pointy sub. And so, as a pointy sub, the for command, which is really just a map, so this is the same as doing this. Right? It's the same as doing that. Map looks at the block. It says, I need 2 values of the block. So it goes and grabs from the list items 2 at a time and then passes them to the block.
Parcels in the list.
They would be flattened.
Couldn't you have it be such that if you use parcels, that a one element parcel would go to A and B would be empty in that case?
Not with map. There's another function for that called tree. So in that case, it would probably be something like list.tree, and you give it the block. Or you would convert it to a list of lists and then map that. So you could also do it for list.lol, like that. By converting it to a list of lists, you're preventing them from flattening. So the parcels would become elements that would then be passed to A and B. Yes, it gets confusing. It will be understood well someday.
Yeah, in the case of map, that's more or less how Perl 5 behaves.
Right.
It flattens.
Yeah, original versions of Rakudo had map where it could handle flattening and non-flattening behaviors. And it turns out that having it always be flattening makes a lot of things faster and simpler. And the .lol is to handle the rarer cases where you don't want that to happen. The Maplter class also is the thing that handles the control flow from things like next, last, and redo. It's also the thing that causes the first, next, and last phasers to be invoked. If you don't know what a phaser is, watch more Star Trek. A phaser is a block that is executed when you change from one phase of execution to another. So a first phaser is a block that gets executed the first time you enter a block as part of an iteration. A last phaser is a block that gets executed the last time you exit that block, and there won't be any more iterations. Next is a block that is executed at the end of each iteration.
That's like continue in Perl 5.
Yes, like continue in Perl 5. And so it internally manages a listed or chain to handle that. Range is a very interesting case. Okay, so I've noticed that range is there, and people will say, why is it an iterator? Why would you consider range to be an iterator and not just an iterable or list? This fell out from a variety of things. The early implementations of range had a separate range iterator class. So you had a range, which represented a range of numbers, and then there was a class of object that handled the iteration over those. But there was a ton of coupling between range and range iter, where ranges had to know a lot about what range iters did, and range iters were always looking back into the range to figure out the start point and the end point, or they had to make copies of them and all sorts of things. So I discovered something. I said, wait a minute, range objects are immutable, at least after the spec change that caused them to be.
And cursors are immutable.
And so a range is always going to return the same sequence of values. Right? If you ask it for a list of values, you can't change the range itself. It's always going to give the same sequence. So the reify method for range can easily compute and return values, and the range needed to continue the sequence. So if I have a range going from 0 to 10, and I say, give me 5 elements, it gives me the first 5 elements, 0, 1, 2, 3, 4, 5, or 4, that's the 5 elements, and then what I need in order to continue the sequence. That's just another range. It's another immutable range to be able to do that. So I don't actually need another class to do that. And if I were to ask this range to give me another 5 elements, it comes back and gives me 5, 6, 7, 8, 9, and 10. So having range, I'm sorry, what?
Wait a minute, 10's not a range.
Yeah, the range reification, it's allowed to do more or less, and it's actually smart enough to know, that doing 10.10 is silly, so it just gives you 10. So having range handle its own reification is much cleaner. It knows its endpoints. right? It knows all of its stuff. So as I was doing it with range iter, I finally said, I'm going to stick the reify method in range. And if you go through and look at the things, since range has a reify, things with reifys are naturally iterators. And so that's where I put it in the class hierarchy. If you ask a range for iterator, it just returns itself, as all iterators do. And if as an iterable, it would just return itself. I might decide range really fits to be more as an iterable for some other reason than iterator, and it would still work the same, except it just changes the class hierarchy. But since it has a reify and iterators have reify, I stuck it there, and everything seems to work. Yes. Okay. Any questions on those? I promise that's the end of iterators. Yes.
So when the range changes from 0 to 10 to 5%,
The range doesn't change from 0 to 10 to 5 to 10. It gives you 0, 1, 2, 3, 4, and a new range of 5 to 10, like most iterators do. Iterators don't change what they know. They generate a new iterator of the same type that handles the rest. Yes, it's another range. It's another range.
So in theory, if I put a star on here and I kept getting chunks of it, it would just keep getting new ones with the starting point.
Yes. Yep. It's exactly what it does. Yes.
From an internal standpoint, seems like it's very heavy to do this. Does it already make use of pulling more elements than it needs?
For range, it does. For integer ranges and numeric ranges, if you say, like, I want from 1 to infinity, and then you go and start requesting elements for it, it does like 1,000 at a time. It starts to make the trade-offs there to say, I'm going to really look ahead to be able to do that. And also, we've gone ahead and optimized that particular case because numeric ranges are so common that it actually does it at low-level object code and not in Perl 6 code because it's common. It makes it really, really fast. So that's an optimization we've done. Any others? Okay.
The nice thing about range is you know the type of the endpoint, so if the fit into low-level int,
Yes, exactly.
yeah,
Alrighty, so handling infinity. So iterable objects have an infinite method that report finiteness. Is the thing that's iterable finite or infinite, right? And there are 3 possible answers. True is I'm infinite and I know it. False is I'm finite and I know it. And mu, which is another type in Perl 6, is actually the parent of any, says I don't know. I might be finite, I might be infinite, I haven't figured that out yet. But when I figure it out, I'll report differently, right?
could have used 42.
So, these are the 3 possible values. Now, all 3 of them are really needed for good reasoning. So, if I have a range from 0 to 5 and I say, are you infinite, it comes back and says false. We know that to be finite because the endpoint is finite. There's a finite number of elements there, and it can detect that. If I say I want a range from 0 to infinity and I ask if that range is infinite, it comes back and says true. My endpoint is infinity, so I know that if you ask me to, I'll generate enough elements for you until you get tired of asking. Right? So those are pretty easy cases. If I have a sequence, this is the Fibonacci sequence again, and I say I want the numbers 1, 1, the previous 2 numbers added together all the way up to infinity and ask if it's infinite, it will come back and it will say true. And it will say true because of this star here that the programmer put there. If you put a star at the end, that implies infinity. And the sequence operator can determine that. But if you say 1, 1, star plus star up to 10, the way the sequence operator works is that it stops when you reach this point exactly.
That's one of the values that comes back.
It's not. And the thing is, the sequence operator can't know that because this is an arbitrary generator as far as it's concerned. It's a block. So the sequence operator can't know that you're going to reach an end because it doesn't know, it can't introspect to figure out what you're computing, and it doesn't know that that sequence, since it's arbitrary, would ever absolutely match that value.
It doesn't know you need greater than, it has to look for an explicit match, because the sequence might not contain that value.
Exactly. So
It
therefore,
might generate
perspective.
11, but it doesn't know.
Right. So And actually, if you were to save the sequence, it would actually not stop at 10. It would go to 11, and then the other ones, or 13, I guess, is the next one. So
We tried doing it the other way.
it didn't really work. I have a question here.
So why
Mu isn't undef. There are many values of undef in the Perl 6 world. It's a type object, and mu is the most undefined. It will continue on forever because you will never match that endpoint. Okay? Yes, here? It's not actually using equal, it's using smart match. You can put things other than values there.
Unlike in Perl 5, smart match actually makes sense.
Yeah, it's using smart match, and I don't want to get too far down that, so I'll be glad to answer that here. I know I'm like out of time. I'm going to take 2 more minutes just to finish infinity. So if you have a list and you ask if it's infinite,
Good one, yeah.
a list delegates infinite to its list iterator. By the way, infinity explains why it's taking so long for us to build Perl 6. So if you have a list and you ask if it's infinite, it just asks its list iterator. A list iterator, to determine infinity, just looks at the next thing in the sequence that it hasn't processed yet and asks it, are you infinite or not? And if the thing comes back and says false, then the list iterator says mu, because the other things might be infinite. If it comes back and says true, it knows that it's infinite because the first thing said it did. We could scan ahead for those. I haven't implemented that yet. And when you're reifying a list, and you're doing it eagerly, it stops when it finds an iterable that says, I'm infinite. If the iterable doesn't say, I'm definitely infinite, it keeps going, just in case it finds one. So the other thing that's interesting is that map blocks don't always return mu. So mapping, even if you are mapping over a known infinite or a known finite thing, the process of mapping currently always changes that to mu that it doesn't know, because the block could change what happens. An infinite list could end because of a last. A finite list could go forever because of a bunch of redos. And so mu kind of, mapping always reports mu for that. And we might change this as we do some experimentation, but that's the safe choice for now. It causes the list to not exit. Gather infinite also reports mu for similar reasons. We're working on a syntax to explicitly indicate infinity. So if you have a gather statement and you want it to be treated as infinite, then you can put a comma star there and do that. That's not implemented yet, and there's still some details to be worked out. I wanted to do slicing, but I'll have to do that another time. And a bunch of other things here. So come to my third talk, which will be at next year's YAPC. Or I might even do my third talk at YAPC Europe. Come there. Yeah, do it as a lightning talk. So summary, there's lots of considerations. Doing lists is hard. And these are the reasons why. Figuring out the immutable iterators was the key to doing it. Here's some of the key roles. I don't have time for questions, so meet me in the hallway track. I'm free for the rest of the conference. Thank you very much.